So quite appropriately, today we have a speaker from the US, and it's Stella Schindler, and she will talk about PT and patterns in finite density QCD. So go ahead, Stella.
All right, thank you all for having me here to talk. I know this sounds like a very collection of topics to put together. PT symmetry, pattern formation, finite density, QCD, but it turns out they're all intimately related, and it's we're going to find out that there's pattern forming phases in effective models of finite density QCD that arise from PT symmetry. So to get there, though, we're going to have to go through a lot of different concepts. We're going to borrow things from many areas of physics, so hopefully there's a little bit of something for everyone. I know this is a diverse crowd, so let's get started. So I guess let's start with the physical motivation. So one of the big long-standing problems in nuclear physics is trying to find the QCD critical endpoint. So if you look at the QCD phase diagram and what we expect for it, can you see my mouse?
Yep.
Okay.
Yes.
So normal matter, what's around us every day, is hadrons. So you have quarks confined inside a proton or a neutron, or other baryons and mesons. When you get up to really high temperatures and densities, though, you end up going to a quark-gluon plasma. So this is like in the first fraction of a second of the universe, or inside really dense matter like a neutron star. Think about like putting the mass of the sun in an area, a sphere with the radius of New York. And we expect that there's going to be a first-order transition from the hadrons to quark-gluon plasma. And people think they have seen hints of evidence and experiments that this is the case. And we know that this critical line does not continue over to the y-axis here of temperature. So you would expect that a first-order critical line would terminate in a second-order critical endpoint. And people have been looking for this. So experiments so far right now, Rick, the relativistic heavy ion collider at Brookhaven, they're doing scans around 100 MeV going up the y-axis. Haven't found anything yet. There's going to be another experiment coming online at FAIR, the compressed baryon matter experiment at FAIR in Darmstadt. In a few years, they're going to be looking at this sort of going up a diagonal, seeing if they can see anything, but nothing so far. Theory, of course, QCD is non-perturbative in this region. There's a running coupling constant. It gets too big to do perturbative physics. So you'd think the next thing you do is put QCD on the lattice and try to look for things, but it turns out at non-zero density, you run into what's called a sign problem to simulation. Now, people have tried to circumvent this in various ways, Lefschetz symbols, the complex Langevin formalism, things like that, but there's been no success so far, so we're sort of stuck. What do we do? Conveniently, finite density QCD is PT symmetric. So if we can find out a little bit more about PT symmetric quantum field theories, maybe this will give us a hint to what's going on. But before we get there, first we're going to do a brief review of PT in physics. I know you've heard a lot about this already, so I'll just speed through. Then we're going to be playing around with a simple, non-trivial PT symmetric quantum field theory and seeing if we can figure out what's going on. And we're going to end up seeing these pattern forming phases in the critical region. And we're going to want to get to the bottom of this. So we're going to do simulations first. Then we're going to try to do analytics to figure out what's going on. We're going to figure out how to interpret non-Hermitian instabilities. This will lead us to formulating more general formalism, figuring out whole universality classes that have this pattern informing critical behavior, and PT symmetric lattice models of QCD are going to be in these universality classes, and I'll show you how to look at a few effective models and find the phase diagram of those models. So this gives us a new path forward for finding the QCD critical endpoint. It's really cool. So let's get started. PT symmetry, we've all heard everything about this already, all the basics. You have a P operator, a T operator. P is usually going to be X to minus X in a quantum mechanical system, but in the field theories we're looking at today, importantly, we're going to take phi to minus phi. We're going to have one of the fields have the parity symmetry, not the position space variable. So we end up with an action that looks like this. So, PT, of course, has been very well explored in quantum mechanics. Quantum mechanical operator that's Hermitian, of course, has a real spectrum. You can have that in an unbroken PT system. You have a positive norm, you have unitarity, orthogonality, interlacing, completeness, all of these great properties, which you don't have in a general non-Hermitian system. Of course, this has been taken into experiment. So about 10 years after quantum mechanics was first discovered by Carl Bender, one of his graduate students, Dimitrios Christodoulidis and his group came along and said, oh, well, you know, the Schrodinger equation is isomorphic to the paraxial wave equation of optics. So, you know, we can have PT-symmetric optical systems and get things this way. Now, the physical interpretation, how we make a PT system in an optic system, well, the potential in a quantum mechanical system becomes the refractive index in an optical system. And what is a complex refractive index? Well, it's basically just energy exchange between the system and its surroundings. And any system you take, generally, you're going to have, that's not Hermitian, you have exchange of some observable. You have gain or loss. So in this case, when you have a PT symmetry condition, this imaginary part has to be equal to its opposite on the, if you flip it over whatever axis. So you end up with balanced energy exchange. And this carries over into quantum field theory as well. It's going to be how we think about these problems. And I'd also like to point out the first true quantum PT breaking experiments happened a couple of years ago by a group in China and in St. Louis. So high energy theory. We've heard a few talks recently about this from some of the people in this room. And we know that PT quantum field theories have some analogs of conventional quantum field theory properties. Today, we're going to be looking at finite density QCD, and we're going to see these weird pattern forming behaviors that are associated with PT symmetry. And sort of the intuition we want to get when we're thinking about a particle physics system is that instead of this exchange of energy between the system and its surroundings, we're going to have a balance of number density. So the amount of antiquarks and quarks coming into and out of the system are going to be balanced by PT symmetry. So we're going to be looking at critical phenomena specifically. So just one small aspect of everything we could look at in PT QFTs, but very interesting. So first, I'm going to tell you how to simulate PT field theories. Now, you can't simulate all of them, but you can simulate a large class, and that will be useful to us today. I'm going to take a fairly typical model and look at it, and we're going to figure out the behavior of these systems, and then we're going to develop a paradigm for the pattern formation you see in the background of this photo. So, as I told you earlier, with a non-Hermitian system, you're generally going to run into a sign problem if you try to put it on the lattice. What's a sign problem? Well, normally when we simulate a field theory, we're going to have to do averages over a set of weights. And if you have weights of two different signs, so the sign problem, so if you have positive and negative, there's no computationally efficient way to do that. And it ends up being non-deterministic, non-polynomial hard. So this is a major obstacle in lattice field theory, which has really hindered the development of, studying the QCD critical endpoint. And of course, it's not just negative weights that have this issue. It carries over into complex systems. So we face the same issue in PT symmetric theories. So, but PT systems, as we all know, are a very nice subclass of all non-Hermitian systems. And oftentimes they have properties that we can use to really do cool things. So we want to simulate some Euclidean path integral with some action. This action is going to be PT symmetric. We're going to need positive weights to simulate it on the lattice. But conveniently, any function you take that's PT symmetric, the Fourier transform of that is always going to be entirely real. And if you take a real function, you end up getting a PT symmetric function out if you take the Fourier transform, which is a really convenient property. It's not guaranteed to be positive, but large classes of these systems are going to have positive Fourier transforms, which means that if we take the Fourier transform with respect to this variable phi or some field that the PT symmetry is in the action, then we're going to get something real out and hopefully something positive. Are there any questions so far? No. All right. So I'm going to take a model. It looks sort of like conventional phi to the fourth theory, except we're going to stick in this PT symmetric term, this quadratic term here, where you've got some non-trivial coupling with a strength of G that's PT symmetric between the fields phi and chi. Chi is going to be a massive field. This is the one with PT symmetry because we're going to stick phi in a double well potential. And this double well potential, we have this term H phi, which is not PT symmetric, where we can raise and lower the potential and sort of get rid of this symmetry across the axis. And this is just a sort of arbitrary model we've chosen to simulate and try to figure out basic PT field theory behavior. We're going to see how this interaction changes everything. So it was first looked at by my collaborators for H equals 0, and now we're going to extend it to the full GH plane of this coupling and moving up and down the well. So when we want to simulate this field theory, as I mentioned, we're going to take the Fourier transform of this function with respect to the PT symmetric field chi. So we're not taking the Fourier transform with respect to x and getting some position space variable omega that turns into a frequency. We're taking it with respect to chi. So this pi mu term is going to be conjugate to chi. You do a little bit of integration by parts. We're integrating the path integral, of course. We're doing the Fourier transform. You get this d dot pi term. It's pretty simple. If you look at these papers, it works out the whole transform. And we're going to be able to put this on a lattice because, as you notice, this is entirely real and positive. Okay, so when we look at these field configurations, we end up getting these nice, weird pattern-forming behaviors. So, of course, the way we do simulations in lattice field theory, we do Monte Carlo simulation. So we're just sort of, doing a random walk around space. Of course, you can put in Markov chain Monte Carlo and make things quicker and better. But we're going to use this set of parameters. So we're going to set m chi to 1/2, lambda equals 0.1, v equals 3. These are just arbitrary parameters we've chosen where we get nice patterns. We're going to put it on a 64 squared lattice. We can do this in any dimensionality, actually. So you can do it in 3D also, but for the purposes of a talk, this is hard to visualize and explain. We have what's called a lasagna phase here, where there are these sheets. You can also get gnocchi phases, little balls, spaghetti phases in 3D, also in 4D, but it's just very hard to see. So it's going to be very hard to analyze and talk about. So I'm going to be talking about 2D models like this. And you'll notice that the patterning here violates spectral positivity. So this is something that's unique to PT systems that we don't have in a conventional field theory. And these patterns, you should believe them. These are at equilibrium. I've sort of shown you simulation time here. We've done a hot start plus about 20,000 sweeps. So here's I guess the difference between a hot start and a cold start. You see they both equilibrate fairly quickly. So out in the region we're analyzing with these patterns, things are pretty steady. So we know we're in equilibrium. So what is pattern formation in physics? Before I get into the model we're analyzing, patterns are a fairly common thing. So you see them in condensed matter physics, you see them in biophysics, you see them in astrophysics, all sorts of crazy systems. And why is this such a common thing? Well, it's induced by competing forces. So you have repulsive and attractive forces that are competing. You end up getting pattern formation because there's this competing between the fields wanting to be at high value, low value. So you end up with these weird forms like dots and stripes. Now, why do we get pattern formation in a PT field theory instead of like a conventional field theory? Well, the PT couplings make the scalar exchange repulsive. So we have these competing forces, and you can also have pattern formation in purely repulsive systems. And these have been well studied for dozens of years. And traditionally, the paradigm that we use to describe a pattern is pasta. So I'm borrowing some language from nuclear pasta here, which is a phase in the inner crust of a neutron star. You can have spaghetti or gnocchi and all these different phases. And they're characterized by high symmetry shapes. So here we have mostly dots. So, and we expect that these pattern phases are going to be separated by first order transitions. So you might have dots in one region and then they transition over sharply to a striped phase. And you can solve for which ones are which by minimizing the free energy of the system. But this is actually not what we're going to find in our models. And we're going to end up developing a new paradigm for pattern formation. So when we look at our simulations, so we've run like 50 of these. We have an enormous set of data. And I'm just showing you 9 of them to explain what's happening here. So at the top here, you notice we have shapes that are sort of lines, spaghetti-like shapes. And then they start breaking apart as you increase the H value and move over. And eventually in some region, we don't have patterning at all. You can sort of think of this dark blue phase. These things are just small fluctuations where it's a little bit lighter of a blue. When we go down, the characteristic width of these patterns decreases, so they get thinner. And eventually you're just going to end up with this blobbiness and then eventually go out of the patterns region. So breaking apart of the patterns, going this way, and then that way thinning out of the patterns. I don't see microphases in this. I see many different phases and shapes in each configuration. I see some dots here, some lines here. Same thing down here. There's a smooth variation of these patterns into one another as you keep fine graining this and getting patterns that are closer together. There's a smooth variation of the order parameter, the expectation value of phi, and there are no microphases in this. So this looks like one phase. And a way we could sort of describe this is like an arrested spinodal decomposition. So spinodal decomposition, normally it's a time variable. In this case, we're moving the parameters across or down in H and G. So this is a name we're putting on it. Now, the interesting thing, though, that gives us a hint of where these patterns come from is if we take the Fourier transform of the configuration. Now I'm doing this in the position space variable x for the patterns, and I'm Fourier transforming them over. So the ring, as we notice, only corresponds to the pattern phases. And in this one in the top right corner, there's no ring. So what does this mean? So the microphase model tries to distinguish gnocchi from spaghetti, from lasagna, from all these other phases. But really all the patterning arises from this single ring. And that suggests there's a unifying mechanism that's best understood in momentum space for why these patterns are occurring. And like if you take a normal conventional field theory that you'd study, the propagators of a Hermitian, one of these systems, have poles in their stable phases at k squared less than 0, so you're not going to see the rings anywhere. Like the correlation between the different parts of space is not, it doesn't decay exponentially. Here, only in these PT systems do we have this persistence of the rings in momentum space. So what's going on? And that's what we're going to try to figure out next.
Stella, can I ask a question about the rings in your patterns? Just on the, that's right. They look actually a little bit like polygons rather than rings. Is that just my eye, or I mean, it looks, for example, like I see 4-fold symmetry and 8-fold symmetry. And things like that.
So Carl, what you're seeing is actually a sign of the underlying lattice. I mean, it's a 64 squared lattice, but
right.
There is, particularly as you get out to the edges of the patterning phase, you see these lattice artifacts, and it's actually kind of squared off shape. And, we have other, simulation runs that, very clearly show, those lattice artifacts.
So it really is, what you're saying is it really is a ring.
Yes.
Yeah, it's distorted a little bit on the lattice, but if we're pretty sure that if we went to a larger lattice, it would go, those effects would go away.
Okay.
May I ask you
just lattice, you get higher runtime. Oh, was there another question?
Yeah, I have just one question, because I think I read you another article where you considered the model which was not PT, not kind of non-Hermitian, it was not PT symmetric, but it was just the model with short range repulsion, as far as I understand. And you got also similar patterns, as far as I remember. so basically the same patterns, but not from PT symmetric models, but just from, say, models with some short range Yukawa type of interactions. Was it?
So were there non-local interactions in this? Because you can always like recast a PT field theory into a real looking form. And I guess like, I don't know, the way you might like distinguish a PT system from a Hermitian system, like you look at them, I'm going to show you in the next few slides. If you look
I just want to say that it looks like this pattern formation is not unique to PT symmetric theories, or you say it's just unique to those theories.
I would say that I would think that any real looking field theory, you might be able to cast it into a PT symmetric form, particularly if they're non-local interactions. That would, there's probably some underlying PT-ness, because like, of course, the astrophysical models that have pattern formation, like the nuclear pasta, have these non-local interactions. It looks real, but I would say there's probably some underlying non-hermeticity, and you can't really look at a field theory and say this looks very, you can't really pick out which one is going to be like a PT system just by looking at it. And I think when we look at these mass matrix eigenvalues and things that are going to cause the pattern formation in a few slides, you might be able to analyze one of these real looking systems in that way and recast it into a form where you have the local PT symmetric interaction. And that's what.
Okay, thank you. Thank you.
Ask again in a few slides if things are not making sense. That was a very good question. So let's go to analytics next. So what we've seen so far, let me just step back and review. I've shown you how to simulate a PT field theory, or large classes of them. You can't do all of them, but you can do a lot. We've put it on a lattice, and we've seen weird patterning behavior that's persistent in this region, and it's associated with these ring instabilities, these tachyonic instabilities. So this suggests that we look at the propagator and momentum space and see if there's anything weird going on we can associate with PT symmetry. So if we look at the phases of this PT extended phi to the fourth theory, so I'm just going to remind you of what our action is. We've got this double well potential. We've got an imaginary coupling between the two fields. It's this multi-field model. I'm going to do this for you in one way right now, and then I'm going to show you a different way of doing it later on, which I highlight in yellow down here. So basically, we can integrate out chi to get the effective action. We've got this non-local term here, and this real local term. We're going to find the order parameter that minimizes the effective potential. This is just something we can read off the effective action by going to zero momentum. And then, so these non-local terms are going to work against the quadratic terms in the action to break the symmetry when we look at the propagator. So I've written the propagator here, the tree level propagator. We're going to look at it on the next slide and be able to draw the phase diagram from that. This is equivalent to minimizing the potential directly from the action from the matrix propagator. So we can do this generically, and I'm going to show you that later for a different system. So this propagator, where things are going to go bad is where it's zero, because this is the inverse propagator, so we want to look at the poles of that. So you end up getting just a quadratic equation in Q squared. So the way this works is you want the poles to be negative to get your normal behavior you'd see in a normal quantum field theory. And you get instability. You have one that's negative and one that's positive. It's a PT propagator, so of course we can have complex conjugate behavior. Both of the poles are going to be complex conjugates, but this is actually not that sick. So the propagator still decays exponentially. What's going to be weird is it's going to sort of decay exponentially and go up and down a little bit with sinusoidal modulation, but we don't expect that this is going to make the simulations we do look too much different. So the normal and the PT broken regions are just nice normal, and then there's this unstable region that's badly behaved as we would normally expect in any field theory. Now, the interesting part is that if you have two positive poles, then this is unstable at perturbations with q squared equals this poles. So you've got that ring shape, but it's stable against perturbations at q squared equals 0, which this is just a manifestation of a thing that's commonly in the literature, a Lifshitz instability. So while the homogeneous phase is unstable, the stable phase is one that's inhomogeneous. So you get these patterns. So even though you might look at this and you'd say this is unstable, the only thing that's unstable is a homogeneous phase, just a flat, like that dark blue phase we saw, and you get the patterning. And this really ties into those patterns we've seen, the fact there are no microphases, because there's just one condition on why these occur, and it matches up with these ring shapes we were seeing in Fourier space in the simulations. Is everyone clear on this so far? Are there questions? Let me show you the phase diagram for this. So the phase diagram, so first here in the G phi plane, we can plot just these quadratic things we saw on the page before. There's very good agreement with simulations. So the patterning region is where we'd expect it to be based on those patterned configurations, phi configurations I showed you before. Now, where is the critical point in this model? Let me figure out how to draw on here. So critical line runs up here, all the way to where the pattern phase hits the unstable region. Now, the boundary between the patterned and unstable regions is the disorder line. If we cast it into the GH plane, which is the phase that we originally had things in, so with the GH parameters, we of course don't see any instability in our simulations. And of course, the critical endpoint is going to be at the exact same point up here where it was there. I didn't draw it super well, but it's going to be inside the patterned region. In the G5 plane, it's going to be on the patterned region. This is fine because the critical line is just a branch cut. So really here, what we've done is all we had to do was analyze the propagator. And this is enough to figure out where these patterned regions are. And the critical endpoint that we're looking for is always going to be associated with the patterned region. So are there any questions about this?
No.
All right, moving on. Now, how do we make this general? So we're talking about critical behavior, and sort of the first thing that comes to my mind when I think of critical behavior is universality classes. So basically what these are is that quantum field theories that have the same sort of global symmetry and dimensionality have the same critical or similar critical behavior, similar behavior in the critical region. So like the classic example is that the Ising model has the same type of critical behavior as a Hermitian phi to the fourth theory, and really more generally, all Z2 models with long-range interactions. If you try to tack on some sort of long-range interaction to that sufficiently long range that'll bring you into a new critical region or a new universality class, there's a whole theory of crossover about this stuff, but we're not going to worry about this today. We're just going to look at, we're going to take standard universality classes and we're going to tack on a PT symmetric term. So these PT effects, they change the phase structure away from standard behavior. And then the crucial way they do that is by leading to these complex poles, these tachyonic instabilities, the patterning behavior we can't have in a traditional Hermitian field theory. And we've done this for one simple Z2 model already. I've shown you the 2D. We can do this for any amount of dimensions. The analysis we did was fairly general. And now we're just going to take this to the most sort of general PT scalar field theory you can think of. Okay, so what does a generic multi-field PT quantum field theory look like? So let's just put some amount of fields down, some amount of phi fields that are like the phi fields we looked at before. They transform trivially under PT. It's just like a Hermitian field. It's going to be coupled to a field chi that's non-trivial under PT. And we're going to have some symmetry group G. So with Z2 before, we could do it with ON or whatever you want to put on there. So we're just making it very arbitrary, as generic as possible. So we're going to analyze the potential as we did before. So let's just call the minimum just phi naught, chi naught. So that'll be the notation I use. And of course, if this system has an unbroken PT symmetry, then phi naught is going to be real. Chi naught is going to be imaginary. So the potential is going to be real at the global minimum. So this is just the pure parallel of what we had before for the PT extended phi to the fourth theory. So now let's try to draw the phase diagram. So the zeros of the mass matrix plus this term here, just the momentum, are going to be the poles of the matrix propagator. So that's going to tell you what has exponential decay, what's unstable, what's not. So when we write out this mass matrix here, it's going to have a symmetry. So before, when we had just a 2D system, a 2D mass matrix, this was like a Pauli matrix here that it was symmetric under. Here it's going to be just any sort of generic, sigma is going to be any sort of generic diagonal matrix with entries that are plus or minus 1. This means that M and M star have the same eigenvalues. And because M and M star have the same eigenvalues, that means the eigenvalues are real or complex conjugate pairs. So this is PT, this is exactly what we want. We're going to end up with zeros or poles that can be either complex conjugates or entirely real. Because it's not a Hermitian system, we can have negative poles and all sorts of weird behavior. So what do we get? So if the determinant of M is negative, of course, things are going to go bad. It's going to be unstable. And we get the same thing happening if we have a positive determinant of M and some odd number of zeros of this determinant are positive. We're going to get this exponential growth in the propagator, which means things are just poorly behaved, unstable. Now, if all of the zeros are negative, then we're going to get exponential decay of the propagator, which is just sort of the normal thing we see in any normal field theory. If some of these zeros are complex, then it's going to be like a PT broken region, and the propagator is going to decay still, but it's going to be the sinusoidal modulation, but nothing sick about that. It's just sort of like a normal region. Now, if you have an even number of poles that are positive, then this is going to be stable with respect to the q squared equals 0 fluctuations like before. It's going to be unstable with respect to these sort of pole ring tachyonic instabilities, and that's going to lead to patterning, just generically in any sort of PT model. So we'd expect that out of PT quantum field theories, this is going to be a universal behavior, this patterning, and it's just something you're going to get just purely out of the structure of this mass matrix. And you're going to be able to, this is just a generic way to compute where this patterning occurs analytically. Which is always going to be in the critical region. So we're going to call these PT universality classes. Every conventional scalar field theory you can tack on a PT term, you're going to get something where, with the right range of parameters, you could get this patterned phase. Why is this? Well, the eigenvalues of the propagator, they're going to be, like if you have two negative roots inside the patterned region, then whenever you come into the region, you're either coming from one root or two of the opposite sign. So one of them is always going to go through a 0. So this is going to be by a critical point, all this patterning behavior. So the critical endpoint is always going to be associated with that. So this talk, I've already shown you a Z2 model. There is a model in a form, sort of like the question earlier, where it was not analyzed in a PT symmetric formalism, but it was a PTON model. We can map it onto that. And they predicted that there was patterning behavior. It was out of Steve Kivelson's group. So there are other systems like this out there that have been analyzed, just not using this formalism. And the really cool thing we can do is we can just predict where the patterning behavior occurs. Sort of just as an aside, one of the interesting things about this model is I think there were pure stripes predicted. So it's like this sort of microphase sort of thought to it. So why are there pure stripes? Well, one way to sort of think about this patterning being a single model, I'm sorry to harp on this, but the paradigm for it of microphases. It's sort of like the distinction in phase dynamics between spinodal decomposition and nucleation and growth. Spinodal decomposition, you can think of it as looking like the patterning. Nucleation and growth, you have these bubbles that form and then grow. And classically, those were thought to be two separate processes, but it turns out they're one and the same. So here, it's just different regions. One might look like a better description than another. So here with this striping and these microphases, you can sort of think of it the same way. The arrested spinodal decomposition is definitely what you would call it in one region. It might look like microphases in another, but really there's no sharp distinction between the two. Anyway, the point from this slide is, though, PT universality classes, you can just construct all of them that have pattern phases, and you can analyze them in this way. So now we're going to come back to where I began this talk. And that's at finite density QCD. We can't do full-on QCD, so I'm going to take effective models and show you what's going on. But this will get us closer to where we want to be, which is cool. So what does QCD look like? So I've already shown you the phase diagram. We're interested in this transition from hadrons to the quark gluon plasma. And it's a first order line with a second order critical endpoint that we don't know where it is. So the SUN Lagrangian, I mean, the number of colors is 3, but many people analyze it just using a general M. Here's your Lagrangian. You've got a Fermion term. You've got a gluon term. Here's a gluon field strength tensor. You can express it in terms of the quantum field for the gluon, and these structure constants. And then, of course, you've got a chemical potential coming in here in the Fermion derivative, covariant derivative term. So when we stick this on the lattice, what happens? So you have an integral over gauge lengths, these quark fields, and then e to the minus action. So this splits apart into e to the minus standard Yang-Mills term. And then you have this Fermion determinant. And this Fermion determinant is where things go haywire because it has a sign problem. It's got this chemical potential, which is complex. So this sign problem, normally in a lattice paper, you'd see it expressed in this way. It's got this nice symmetry, but what can we do about it? It's a sign problem. It wreaks havoc on simulations. But in the real world, the chemical potential, this density here, it's real. So just get rid of that complex conjugate number there, and you see it has just a very clear manifest PT symmetry. And that's why we can play around with it and do all sorts of nice things and try to find these pattern regions near the critical endpoint, which is very nice. So as I said, we're going to be using effective models. You could go either top down or bottom up. Just sort of start with the key ingredients like we did earlier, take a Z2 model and analyze how it works, or we can use more QCD-like ingredients. Today I'm going to be using Polyakov loops, which appear in many effective models that people like to analyze. So a Polyakov loop, which is also called a Wilson line, it's just like the phase factor when a heavy quark is sort of sitting there and traverses a closed loop. So it's periodic boundary conditions, so it's the time, the Euclidean time, is going from 0 to 0 here. And it's just an integral over this gauge, the fourth component of it. And you can express all sorts of quantities you might want to find in terms of this Polyakov loop. So like the energy of a 2-quark state, so quark, anti-quark would be this. You can replace the potential here, the quark anti-quark potential with the quark-quark potential, and just stick in a W instead of a W dagger here and get the quark-quark. Very convenient for using in effective models. So we're going to take things really simple. Instead of using continuum quarks, let's use a static quark on the lattice. How does it contribute to that Fermion determinant term back here? Well, it's going to contribute a factor of 1 plus this constant factor times the Polyakov loop. Then an anti-quark, let's take the Hermitian conjugate, you get 1 plus e to the minus this stuff times the conjugate of the Polyakov loop. And we're just going to ignore this term for now. It's suppressed, it's exponentially small, so it's not going to contribute anything particularly interesting. And for simplicity, to get a nice result to write down on a slide for you here, we're also going to make the mean field approximation. Instead of having this big matrix, we're going to take just some scalar function times the identity matrix. So then we can write down a Fermion action. Now, so what the fermions contribute to what we're going to look at is this term here. So I'm writing this e to the beta, this constant term is just a factor of z to make things look simple. We've got our Polyakov loop. There's a logarithmic term. And then I've also added in factors for the spin degeneracy, the number of colors, and the number of flavors. Now, how are the gluons going to contribute? So first, I'd like to parameterize the Polyakov loop as e to the chi plus I phi, and e to the chi minus I phi for the conjugate. So then these phi and these chi fields are exactly like we saw in our Z2 model. They'll be what we're analyzing that are going to have this PT property, and we're going to be able to find what's going on. So phi and chi give rise to attractive and repulsive interactions between px and py, so between two terms. The attractive and repulsive interactions, of course, we know give rise to patterning behavior. So we're interested in behavior near the critical point that we know is going to occur because there's this attractive and repulsive interaction. We really only care about quadratic fluctuations around the equilibrium values. So if we make this approximation in the critical region, sort of the simplest choice we can look at, which is what I'm going to show you for the next few slides, are these Yukawa potentials. So this would be your gluon contribution to the action, and of course you have to add on the fermion contribution, and then you just have your full action. All it is that. More generically, we can just express any sort of potential we want. We're going to separate it into repulsive and attractive pieces, and then we can split it up into these two terms with chi and phi. And I guess really just to reiterate things, this I phi term is going to change the scalar exchange for the PT particle into these. It's going to change the sign of the interaction, which is what gives us patterning. And that's really the crucial thing to take from this. So what is the full model? Let me just write this out. This is this green one down here. So you've got this fermion contribution, where z is just the e to the minus beta. It's the constant. E to the chi plus I phi. And then you've got this gluon contribution that's generic. This has actually been studied before by Parks and Fisher. They were studying the liquid-gas transition for z is greater than 0. They were really interested in sort of these hardcore repulsion effects when z is less than 0, and they showed that the critical behavior there is in the I phi cubed universality class. So we're not the first to analyze this. We're certainly not the first to point out that there's pattern formation in models like this. I'm sure it's been rediscovered time and time again by different people in like condensed matter theory, particle physics. So what we're going to do, though, is use this PT symmetric formalism to analyze the patterning, and this is a QCD-like model in our approximations. So going back to this Yukawa model to start out, how do we get the pattern formation? So the equations of motion, we can just write down. Standard procedure. If we play around with these guys a little bit, and we're going to set big phi equal to chi plus little I phi. So just subbing in that term, this z e to the chi plus I phi, it reduces this to the z e to the phi over 1 plus z e to the phi term. These colored fermion factors, and then you can reduce things and get this nice equation for the homogeneous solutions. You can solve it, numerically plug it into Mathematica, and these are sort of the minimums we want to get and plug into our potential, which will give us looking at the small fluctuations about that will tell us what's stable, what's unstable, and therefore what are the normal, the complex, the patterning, and the unstable regions for these functions. I've only got a few minutes left, so let me go on and show you the phase diagram. So for the simple quark gas, our phase diagram looks like this. So in the NT plane, we have an unstable region. There's this disorder line where it touches the patterned region. We're going to have a critical endpoint going up here and a critical line. There's a pattern forming region, and then there are these complex and normal regions that behave the same. We can do a quick transformation of variables to sort of these original variables we were using, the chemical potential and the temperature. And we get something that looks very similar to the model we studied before. Why is this? It's just, they both have this ET symmetry. So by universality, we'd expect that these models look similar in their phase behavior. And we can just easily calculate where the phases are, where the different phase regions are, where the critical endpoint is, using the formalism we developed before. And this has phenomenological applications. Now that we've seen this, why don't we try to do the full model? So now we have this fermion term. We have the gluon term. We have this general potential where we have this attractive potential and a repulsive potential. So we go through the exact same steps again as we've been doing this whole presentation. We look for the pattern forming region, which we know is where the critical endpoint is. And we can write down just a general criterion for where that occurs. And notice I'm putting in the substitution for the number density. I'm writing it here. And when we write it in this form, this is actually an incredibly simple form for where pattern formation occurs. All it is, it's just in terms of the Quark potential, beta, standard factor 1/t. And also this factor that's the Quark number susceptibility per site. Because these are all sort of common things we see in a field theory, we can easily just generalize all of these factors to the continuum. We write the Quark number susceptibility per site as just the Quark number susceptibility chi per unit volume. And interestingly, both of these are computable on the lattice at u = 0. There's a sign problem at higher values, but presumably if somebody could circumvent the sign problem in those cases, find some neat trick, these are all numbers we can just compute on the lattice. And that would give us a simple estimate of the critical region. So right here, we've written down something we could potentially calculate and guess where the pattern formation occurs. Of course, this is a simple model. We could extend it even further. We could build in something like triality, because we've, of course, ignored like the diquark interactions here. And we can go ahead and do that, but we only have 3 minutes left. So I'd like to go to conclusions and wrap up what I've shown you. So I started out by reviewing how to simulate a PT symmetric quantum field theory. The introduction. This allowed us to simulate a PT field theory that exhibited patterning. We looked at where these patterns occurred. We took this enormous set of data. We looked at it and we developed a new paradigm for pattern formation. We saw that it was a single phase. Patterning is a single phase in these PT systems. There are no microphases. And it's associated with these tachyonic instabilities, this ring shape and momentum space. Then we were able to look at the analytics and figure out where this tachyonic instability was coming from. We were able to interpret it. We saw that the PT broken region and the normal region, they just have the normal behavior we'd expect. There's an unstable region where the poles behave in a certain way, and things are all bad and unstable everywhere. But one region that we might have thought was bad, it's only bad at the q² greater than 0, these tachyonic instabilities. And we were able to interpret that as the patterning region based on our simulations. So simulation confirms analytics in this case. This allowed us to define new universality classes of PT symmetric systems, of which simple effective models of QCD are part. And we were able to get a simple description of where the critical region of the effective model of QCD was using this pattern forming formalism. And we were able to express it in simple quantities that are computable on the lattice. So in my last minute, I'd like to thank my collaborators. So Mike Ogilvie is the PI on this project. I've been working with my younger brother, Moses, who's a sophomore in college right now and already publishing papers on field theory. I'm home with him right now, so it's been a great thing to do during the pandemic, working with my younger brother. And then, of course, Mike's student, Leandro. And I've been funded by an NSF Graduate Research Fellowship funding from the MIT Department of Physics. And then my advisor's funding is from the Department of Energy. So thank you very much. I'm right at 10. Does anybody have any questions?
Thank you first.
Thank you, Stella.
Questions? I have a question on the patterns. You directly analyze the non-Hermitian model, but you could sort of similarity transform these complex terms away. You know, this I, phi, chi term you had in your first model, you could transform it away. What happens if you then analyze that system? Does it stay the same? Or maybe you haven't done it, but that's a question.
I haven't done it.
Okay.
But I mean, the tachyonic instabilities aren't going to go away. So we've been the simulations come from the real form of this action that we can put on the lattice. That's all positive.
Andreas, I'm not sure you can you can similarity transform it away because of the nonlinear terms in phi.
I mean, the question is general. In usually there's an ambiguity, yeah. So there could be many Hermitian theories related to this. I know that in the path integral, yeah, that's insensitive to the metric for some reason. Yeah, that's magic because it just commutes through. But still, you have to ask the question: why are all these theories equivalent if they are? I mean, in quantum mechanics, we know they are not. Yeah. You understand my question? Yeah.
So
in general, you could.
I don't think you can get rid of this term and make it.
Yeah.
Like.
Stella, can you go back to show the phase diagram of the phi to the fourth model? Yeah, okay. So this is not an answer to your question, but it's a related answer, okay? So, you know, because when you integrate out the PT symmetric field and you get a non-local interaction, it's all a function of G squared. And that tells you that this model is actually a function only of G squared, right? So, because the effective model only depends on G squared. So then the question is, what happens when you analytically continue G squared to negative values? Okay. And the answer is that when you analytically continue G squared to negative values, you turn what was a positive phi squared interaction into a negative phi squared interaction, right? From the extra field. And so you're crossing the boundary from a PT symmetric model to a Hermitian model there. And that's an interesting thing to look at, because it turns out, of course, that the pattern, when you do that analytic continuation, the pattern forming region goes away as it must. Now, I don't, you know, Stella and Mo and I kicked around, you know, how we could use this to think about analytic continuation in the G squared plane, because that's an obvious question to ask. That's clearly related to what you're asking about. But we didn't come up with something that we thought was a good approach.
Okay. Thank you. Any more questions? No more question. That means it was all really clear, Stella.
Thank you.
If there are no questions, then we should all unmute ourselves and give her another round of applause.
Thank you very much, Stella.
I'm going to stop sharing.